So here we have the definition looking at an annuity. An annuity is a sequence of equal payments that are made at regular intervals. So examples of this you do see very often. Okay, so the most simple example we're looking at here, you have a deposit of $100 into a savings account made every week. So if you're trying to save up for something and you deposit $100 in every week, that would be an example of an annuity. Now, on the other hand, what we have is that perhaps you borrow a lump sum amount of money and then you're going to be making payments onto that account. And so you're making payments, let's say, of $400 every month to pay it off. That would also be an example of an annuity. Okay, so now that we have defined what an annuity is, we're going to look at what is the connection between a basic annuity and a basic geometric series. So here we have our first example, and we're going to be relating an annuity to a geometric series using this example. So the setup is that you have $150 being deposited every month for a year into an account, and that account guarantees an annual interest rate of 3%, and that 3% is going to be compounded monthly. And we know that every deposit is going to be made at the end of every month for a total altogether of 12 deposits. Okay, so that's fine, but the easiest way to relate this annuity to a geometric series is going to be sort of with a timeline. So let's suppose that this is our timeline. We're starting off right at this beginning, and we have here our total of 12 months, our 12 deposits. And along the top of this timeline, we have that at the start, we make sort of $0 payment, but at the end of the first month, we make a payment of $150 or a deposit of $150. And we do that at the end of every month, all the way with the very last payment occurring at the end of the 12th month. Okay, so that's fine, but the real question then that we're going to ask ourselves is, how much do we have in the account after every month? So how much is in the account after every month? So let's start by looking at the first month, and we have month 1. Really, we just make the first payment at the very end of that first month, and so we have $150 done. Now, what happens at the end of the second month? How much money will we have? Okay, so here there are going to be two things to consider. So first off, we're going to make another payment of $150. Okay, that's going to be this second payment. But then also, this $50 that we put in at the end of the first month, it is going to be earning interest. Okay, so how much is that $150 going to be worth by the end of the second month? Well, here it will have been in there for 1 month, and it's going to have been earning interest of 3% compounded monthly for that 1 month. So we know that if I want to calculate just simple compound interest, I can use the formula that A is equal to the principal amount, how much has been put in the account at the start, multiplied by 1 plus r over n to the power of nt. Okay, that's our basic compound interest formula, and so we're going to use that right here. We have $150 deposited into the account. It's going to be earning 3% interest for n is 12, because we're looking at here a monthly compound interest rate, and it's also going to be in there for a total of, well, n is 12, but t is going to just be 1 month, so it's going to be 1 over 12. So it's really just one period, and so we don't actually even need to put this exponent there at all. Okay, so this right here, this is going to be the amount that that $150 is worth after it has sat in the account for 1 month. And that's fine now. What we're going to do is take a look at what happens at the end of the third month. So month 3, we put in another fresh $150, and then we also have that the 150 that was put in at the end of last month, it's going to earn interest for 1 month. So from before, we know that it's now going to be worth this much. And we also have this whole amount that has now earned interest for another month. So that's going to be that amount, but it's going to earn interest again. So what I'm going to do is we're going to square that. Okay, so now we have these 3 different amounts. This is the amount that hasn't earned any interest at all. This is the amount that has earned interest for 1 month. And this here is the amount that has earned interest for 2 months. Okay, and we could keep doing this, okay, with month 4, 5, 6, 7, and so on. But the pattern is fairly clear, I would say, at this point. And so what we can do is sort of factor this, okay, to make that pattern even a little bit more clear. And then we're going to extend this all the way through the 12-month period to see what we get by the end. So I noticed that every term has 150 in it. I could start by factoring out that term 150. Now, what does that leave me with? Well, the first term, if I factor 150, is going to leave me with 1. The second term, if I factor 150, is going to leave me with 1 plus 0.03 over 12. And the third term is going to leave me with 1 plus 0.03 over 12, and that whole thing is squared. Okay, so this is what I get technically by the end of the 3rd month. So now let's extend this and see what we would get if we continue this pattern all the way to the 12th month. So by the end of the 12th month, we should have 150. And so I'm going to just take this pattern here and repeat it until we get to 12. So I have 1 plus 1 plus 0.03 over 12 to the power of 1. And then we have the same thing to the power of 2. We would have the same thing to the power of 3. And this would keep going on and on and on for all 12 months. But we want to sort of figure out what's the last term going to look like. Well, it would look like this, but what's going to be here? That exponent. Okay, so here we want to just be careful. Is it going to be 12 or not? Because we notice that after 2 months, after the 2nd month, that exponent was 1. And after the 3rd month, that exponent was 2. So that means that after the 12th month, that exponent is not going to be 12. That exponent is going to be 11. Okay, so we want to be careful with that. We plug that in. And that right there would be what you would get after your 12 months. Okay, except that nobody wants to add up all 12 of these terms. And so this is where we're very grateful that we have looked at geometric series. Okay, because if I focus on just what is in the brackets right here, first of all, this is a geometric series. And I notice that because to get from one term to the next, all that I'm doing is multiplying by a common ratio. So I have here my first term, a is 1. My common ratio r, okay, what I am multiplying by each time, is just going to be 1 plus 0.03 over 12. That's my common ratio that I multiply each term by to get to the next term. And what do I have for n? Well, here n is equal to 12. We have 12 different months. We have 12 different periods. Okay, so this is a geometric series with a is 1. We have our common ratio, and we have n is 12. So we should be able to use what we know about geometric series to figure out what this sum is going to be. So we end up with a times 1 minus r to the n over 1 minus r. That's what we know about the sum of a geometric series. And we have a is 1 minus r, which is this, to the power of n, which is 12, divided by 1 minus 1 plus 0.03 over 12. Okay, and so we could clean this up a little bit, and we will do so because we want to get out of this sort of a nice formula. Okay, so one of the things we can do is actually take this 1 and this 1. They're going to directly cancel with each other. Okay, but now this denominator here is still going to be negative. Okay, so even though the 1's are gone, that negative is still distributed, and our numerator will be 1 minus 1 plus 0.03 over 12 to the power of 12 divided by negative 0.03 over 12. Now here I want to get rid of this negative so we can rewrite it. Let's actually put that negative into the numerator, and what I end up with in the numerator would then be 1 plus 0.03 over 12 to the power of 12 minus 1 divided by 0.03 over 12. Okay, and so this portion, when I go back and look at our geometric series, this portion now we know is equal to this value. So all we have to do is take that value, multiply it by 150, which was the amount of every payment into the annuity, and that's going to give us the total value of the annuity after the full year. So let's go and do that calculation. What we end up with for our total is 150 multiplied by, and things get a bit messy here, but we have 1 plus 0.03 over 12 to the power of 12 minus 1 divided by 0.03 divided by 12. And so we are careful with our calculator. We plug all of that in, and what we're going to get is $1,824.96. Okay, and that's going to be the total amount that would be in the account after the full 12 months. Okay, and now if we generalize this formula that we just found, okay, we're going to introduce a little bit more sort of notation. Okay, the first thing we have is PMT is going to be the regular payment amount. So in this last example, that was 150. And we're also going to introduce FV, okay, because this is going to be the future value. The future value of your annuity, in this case, is just how much was in there at the end of our 1 year. How much was in there at the end of T years. So we have here FV is the future value of the annuity. So FV is future value, and that's the amount at the end of your period of investment. Then we have R. R is the annual interest rate. We also have T. T is going to be the time in years. And we have N is the number of compounding periods per year. Okay, so these are the different terms that we're going to be looking at in our formula, and then all that we're going to do is sort of rewrite this in those terms. So we end up with the amount we have at the end, so future value is going to be equal to the payment, so PMT, multiplied by 1 plus this right here was just the rate, the percentage divided by N, which is the number of compounding periods per year. So it's 1 plus R over N. And then this exponent here is going to be N times T. So that's the number of compounding periods per year is N multiplied by the number of years, which is T. And we're going to subtract 1 from that. Okay, and then that's going to be divided here by R divided by N. So that's divided by R over N. And that horrible looking formula right there, that is going to be what we use to determine the future value of an annuity, okay, over T years. All right. So we know our formula. Let's actually just go and do an example using it. So let's consider a related situation. Instead of doing it monthly, what we're going to do is we're going to deposit $150 every 2 weeks instead of every month. And we're going to wait 18 months rather than a year. And we're going to use an account that has a 5% annual interest rate compounded every 2 weeks. Okay, so the first thing you'll notice here, guys, is that our compounding period on our interest is 2 weeks, and that's the same duration as when we are making our regular payments. They're going in every 2 weeks. The interest is being compounded every 2 weeks. That's very important for this formula, for those two periods to be the same. Okay, and then once that is the case, we're just going to use our formula. We know future value is going to be the amount of our payment multiplied by 1 plus R over N to the power of NT minus 1 divided by R over N. And we're going to figure out what is our payment amount, what is the R values, and so on. So for this one, we have our payment amount is $150. We have our interest rate is 5% annually. It is compounded every 2 weeks, so that's going to be 26 compound periods per year. And the time T in years, 18 months, is going to translate to 1.5 years. Okay? So if we plug everything in, what do we end up with? Well, the payment amount is $150. We have 1 plus 0.05 over 26 to the power of 26 times 1.5 minus 1 divided by 0.05 over 26. And so you're going to want to practice this a little bit. Okay, make sure that you get very comfortable with your calculator figuring out what these values give you. So if you need to, pause the video here, get out your calculator, make sure you plug this in and that you get the same value that I do. What you should get is that this is going to be approximately, if you round it off here, $6,068.91. Okay, so that's going to be the amount, the future value of this annuity after 18 months. Okay, now that's fine. Let's change this question up just a little bit though. Okay, that's the future value if you make your deposit of $150 every 2 weeks for 18 months. So that's fine. We know if we did this annuity for 18 months, we'd have $6,068 at the end. Let's change it up though. What if we wanted to instead just put a single lump sum amount into an account? Everything else is the same. We have the same 5% annual interest rate compounded every 2 weeks. How much would I need to put in at the very start to leave for 18 months in order to have $6,068 at the end? And this is actually a question that has nothing to do now with annuities. Okay, we can remember our basic compound interest formula that the amount at the end is going to be the principal amount times 1 plus R over N. Let's make that R look a little bit different. We have R over N to the power of N times T. And looking at this, we know really that here, A is our future value amount. That's sort of what we want it to be known as. And P, the amount that we have at the start, that's sort of our present value amount, which we'll get to in a moment. But that's sort of what we're looking for right now. We want to know what is going to be the value of P. We know R is going to be our 5%, so R is 0.05. And we have N is 26. And T is 1.5. So we can plug that all in. We have our $6,068 that we want to have at the end. We want to know what is going to be P. And we have our R, our N, and our N times T. So we plug all of those in here and we could solve for P. You end up getting that P is going to be equal to 6,068.91 divided by 1 plus 0.05 over 26 to the power of 39. You get out your calculator for this, and what you will have at the end is P equal to 5,630.8, and that's how much money you would need to invest at the start in order just to earn interest and have the same amount of money after 18 months. Now we're going to look at this, and we know that here we have $6,068. That is the future value of this annuity. This lump sum amount that we have just found, this is what we are going to call the present value. Okay, this is going to be the present value of the annuity. Okay, that's the amount that that future value would be equal to in today's dollars. All right, so what we're going to look at right now is just a little bit more about what this present value actually represents and what we can use as a formula to work with this present value.